This is session B8, Complex Numbers and Complex Exponentials. Last session, B7, was on the Mach-Zehnder interferometer. Today we'll explore complex numbers and complex exponentials. Quantum mechanical wave functions use complex numbers. Phases that produce interference, constructive and destructive, will be represented as in complex exponentials. Lectures to come will use complex exponentials. These are also used in electrical engineering. If you know complex numbers but not complex exponentials, you can skip ahead to later in this video. If you don't want to learn complex numbers or complex exponentials, you can still follow a lot of the quantum mechanics videos, so don't give up. Go ahead and move to the next video. Ordinary or regular numbers that we use every day are called real numbers. These include positive and negative integers, whole numbers, rational numbers, decimals, irrational numbers, square root of 2, cubed root of 61, pi, e, and any sums, differences, products, or quotients of real numbers. Those are all real numbers. In this lecture, the following variables or constants will only take on real values: a, b, c, d, r, s, theta, phi, sigma, and omega. So we might say that a is real, or b, c, and d are real. Or this notation, s is an element of the reals, the set of real numbers. This sort of double barred R is the set of real numbers. For any real number c, c squared, c times c, is a real number that is greater than or equal to 0. Now, in this lecture for multiplication, I'll try to use X or center dot. I don't want to use asterisk for multiplication, as we will use asterisk for complex conjugate later on. Now, this X does not mean vector cross product. There's no vectors and there's no cross products in this lecture. There is no real number whose square is a negative real number. But we can imagine a new kind of number, not a real number, whose square is -1. We'll call this new number the imaginary unit, and we'll name it I, generally lowercase I, well, always lowercase I when I write it. So I squared is I times I, and we said that its square is -1. In electrical engineering, lowercase j will be used instead of lowercase I, but in quantum mechanics it'll be lowercase I, and that's what we will use. We can create a new set of numbers by multiplying I times any real number, b, which we'll write as just bi. Or we could write it as IB, same thing. And we'll call this new set of numbers BI, we'll call them imaginary numbers or pure imaginary numbers. It means the same thing. Now if we square these imaginary numbers, if we take BI squared, that means BI times BI, and we can reorder these, reparenthesize them and reorder them so that we get b squared times I squared. But we know that I squared is -1, so we get minus b squared. B squared is greater than or equal to 0, so negative b squared is less than or equal to 0. So these imaginary numbers have squares that are negative real numbers. We're going to treat 0 as both real or imaginary, real and imaginary, for the imaginary number 0, it has b equals 0. 0 is the only number that is both real and imaginary and also complex, which we'll learn later. This is a possible time to take a break. We can create a new set of numbers by adding any real number to any imaginary number. So a plus bi, which we could also choose to write a plus ib if we wish, where a and b are real. This new number we call a complex number. In this lecture, certain variables or constants will always take on complex values: u, v, w, z, alpha, and beta. So we might say that u is complex, or v and w are complex, or z is an element of the complex numbers, with this particular c meaning the set of complex numbers. For the complex number u equals a plus bi, we say that the real part is a. Real part of u equals a. And the imaginary part is b. The imaginary part of u equals b. b, not bi, for the imaginary part. Real numbers are complex numbers whose imaginary part is 0. We say that the set of real numbers is a subset of the set of complex numbers. Let u equals a plus bi and v equals c plus di for the rest of this lecture. We can add u plus v. A plus bi plus c plus di, it's perfectly okay to rearrange this to be a plus c, which is real, plus b plus di. b plus d is real, so b plus di is pure imaginary. So this is a real plus an imaginary, so this is a complex number. The sum or difference of any two complex numbers is a complex number. We can also multiply them together, u times v. We would get a plus bi times c plus di. And if we multiply this through, which I encourage you to do, you will get a real number, a times c minus b times d, plus a times d plus b times c, parentheses times I. AC minus BD is real, AD plus BC is real, I is imaginary, so this part is imaginary, this part is real, together they are complex. This is a complex number. If you've never done this multiplication before, do it step by step to verify this results. Later we'll see a different way to express the product. If you multiply it out, you'll see that u times v is the same as v times u. That multiplication of complex numbers is commutative. The product of any two complex numbers is a complex number. The quotient of any two complex numbers is a complex number as long as the number we're dividing by is not 0, which we'll see a little later. Addition and multiplication of complex numbers are associative. We can rearrange parentheses. They're commutative. We can change the order, and they are distributive. Let's look at u squared. We know how to do u times v, so we can just substitute in u instead of v, a plus bi times a plus bi, and if we multiply that out, we get a squared minus b squared plus 2ab times I. This is a complex number, So the square of a complex number is a complex number. The result would also be a real number if this part were 0. So if A were 0, in which case U would be pure imaginary, or if B were 0, in which case U would be real. The result is also pure imaginary if A squared equals B squared. So if A equals B or A equals minus B. This is a possible time to take a break. We define the complex conjugate U star or U bar of a complex number U equals A plus BI as complex conjugate U star equals A minus BI. The real part is unchanged, the imaginary part gets negated. So U conjugate equals real part of U minus the imaginary part of U times I. The complex conjugate U star is a complex number. When there's no ambiguity, complex conjugate might be called conjugate or star, and in this lecture, I'll just call it star, and we will use U star for complex conjugation in quantum mechanics, but some books or classes might use the notation U bar. However, the over bar is also used to mean the average of a quantity, so it could be confusing. Quantum mechanics will use star for another purpose. We will talk about that in future lectures, but it will be compatible with the complex conjugate use. If we conjugate something twice, U star star, we get back the original. We can use the complex conjugate definition, A minus BI. If we add a complex number plus its conjugate and we divide by 2, we get the real part of U because the imaginary part canceled out. We can get the imaginary part of U by taking U minus U star and dividing by 2I. The complex conjugate of the sum or product of two complex numbers is the sum or product of the complex conjugates of the two complex numbers. We'll look at the example of a product. The conjugate of U times V is, we already know the formula for U times V. It's this, AC minus BD plus AD plus BC times I. We take that and we conjugate it. Well, the real part stays the same, AC minus BD, but the imaginary part gets negated, so we get minus AD plus BC I. Now, let's take U conjugate times V conjugate. A minus BI times C minus DI, and if you multiply that through, you'll see that it's the same as the expression above. So the conjugate of a product is the product of the conjugates. This is a possible time to take a break. Let's multiply U by its complex conjugate U star. U star equals A plus BI times A minus BI, and when we multiply that out, we get A squared plus B squared. And A and B are real, so A squared is real and greater than or equal to 0, and B squared is real and greater than or equal to 0, and when we sum them, we get a real number that is greater than or equal to 0. So this product, U star, is a real number and greater than or equal to 0, and it's only equal to 0 when A and B are 0. So the complex number 0 times its conjugate, 0 conjugate, is 0. Since that result was greater than or equal to 0, here, it can be the square of some real number. We define UU star as the magnitude squared of U, being the real number a squared plus b squared. We define the magnitude, also called the norm, the length, the absolute value, or the modulus. The magnitude U, which we will show as single vertical bars, the magnitude of U is the real number square root of UU star, which is square root of a squared plus b squared, which is a real number greater than or equal to 0. So the magnitude of a complex number is a real number greater than or equal to 0. The magnitude of the sum of two complex numbers is not the sum of the magnitudes of the two complex numbers. Don't do that. The magnitude of the product of two complex numbers is the product of the magnitudes of the two complex numbers. So the magnitude of UV is the square root of UV times the conjugate of UV. The conjugate of UV is the conjugate of U times the conjugate of V. We saw that earlier. We can rearrange this product so we get UU star VV star. We can then take the UU star will be a number greater than or equal to 0. VV star will be a number greater than or equal to 0. We can split the square root and do the square root of UU star and times the square root of VV star, and that's the magnitude of U times the magnitude of V. And those magnitudes are the square root of a squared plus b squared, and then the square root of c squared plus d squared, and that product is greater than or equal to 0. Let's look at taking a quotient, which we haven't done before. We'll divide complex number u by complex number v, but only in the case where v is not 0. So u divided by v. Here we have u divided by v. We can multiply the top and the numerator and denominator by the same quantity if we wish, and in this case we'll choose that quantity to be v star. So we'll multiply by v star and divide by v star. The numerator ends up being u times v star. The denominator ends up v times v star, which we know is the magnitude of v squared, which is greater than or equal to 0 if v is not 0. The numerator, u times v star, u is a complex number, v star is a complex number, so the numerator is a complex number. The denominator is a positive real number, so the quotient of u divided by v is a complex number. The quotient of any two complex numbers is a complex number as long as the denominator is not 0. Later we'll see a different way to express the quotient. This is a possible time to take a break. Now we're going to cover the complex plane and complex exponentials. As earlier, we'll take complex number u equals a plus bi, where a is real and b is real. So it takes two real numbers to specify what the complex number u is. We can't represent this on a single number line, but we could represent two real numbers on a two-dimensional plane. And we're going to do that, and we call that the complex plane. Here we have the positive real axis, and here we have the negative real axis. And intersecting at the origin, perpendicular to the real axis, we have the positive imaginary axis and the negative imaginary axis. So u is the complex number a plus bi. It has real part a, so we're going to go a on the positive real axis. A might be negative, but graphically I'm assuming a is positive here, though it does not have to be. So we go a units on the real axis, and the imaginary part of u is b. So we go b units on the imaginary axis. So we end up with the point a, b, and that is the complex number a plus bi. I'm showing it in the upper right quadrant here as though a and b are positive, but a could be negative, in which case it could be to the left. B could be positive, in which case it's the upper half, or b could be negative, the lower half. So anywhere in this two-dimensional plane, there are complex numbers. Every point is a complex number. And every complex number maps to a single point on this plane. Now, we have the point a plus bi, the point AB. We can draw in the vertical segment down to the positive real axis, or the real axis. We can draw a line segment from the point to the origin, and we end up with a right triangle because the imaginary axis is perpendicular to the real axis. So we end up with a side A and a side B of a right triangle whose hypotenuse is the square root of a squared plus b squared. Well, that's the magnitude of u. We saw that before. So the hypotenuse here, the line segment from the origin to the point AB, the length of it is the magnitude of u. And there will be some angle in the triangle from the positive real axis to the hypotenuse. We'll call that theta. And then it's clear from trigonometry that the value a is the same as the hypotenuse times the cosine of theta. So the magnitude of u times the cosine of theta. And the value b is magnitude of u times sine theta from trigonometry. So we could rewrite a plus bi as this a plus this b times I. And they both have a common factor of magnitude of u, so we could take the magnitude of u out and we end up with u equals the magnitude of u times cosine theta plus I sine theta. The tangent of theta will be b over a, but we have to be careful because theta could be in any of the four quadrants. And so we can't just take theta equals arctangent of b over a. Cosine plus I sine theta is sometimes abbreviated cis theta, where cis is just an abbreviation for cosine plus I sine. No magic there, it's just words, an abbreviation. This is a possible time to take a break. We will define the complex exponential e to the I theta, where theta is a real number, a real angle, and e is the constant e that we use in exponential functions. We may sometimes write this as exp I theta, but in this video I think I will always be able to write it e to the I theta. So we're going to define that as cosine theta plus I sine theta. So we're just using it as an abbreviation for cosine plus I sine theta. This is Euler's formula. This formula can be proven, but we won't prove it in this lecture. It's enough for us to just take it as a definition. We will see that this obeys some of the properties of the real exponential. E to the I theta equals cosine theta plus I sine theta. That has, the magnitude of that is always 1. You can do the math for that and you will see what its magnitude is. If you multiply it times its complex conjugate. And it has phase angle theta, positive counterclockwise relative to the positive real axis. So if we look at all possible values of theta for that, when theta equals 0, we will get 1. As we increase theta, we will move counterclockwise on this unit circle. When theta equals pi over 2, then cosine will be 0 and sine will be 1, so we will get 1i. As we increase from pi over 2 to pi, we will get negative 1. If we increase to 3 pi over 2, we will get minus I. And if we increase it to 2 pi, we will be back at 1. The magnitude of e to the I theta equals 1, which we can see if we take cosine plus I sine theta and we multiply it by its complex conjugate, we will get 1, and then we take the square root and we will get 1. This is a possible time to take a break. Let's show that e to the I theta plus phi equals the product e to the I theta times e to the I phi. We can work backwards. Let's take e to the I theta times e to the I phi. We substitute in cosine theta plus I sine theta times cosine phi plus I sine phi. We can multiply this all out. It's just algebra. We will get a real part, which is cosine theta cosine phi minus sine theta sine phi. And then an imaginary part, which is cosine theta sine phi plus sine theta sine theta cosine phi, from multiplying it out. Now, you might not recognize it, but these are actually have a fairly simple form from Trigonometric Identities. The real part is just identical to cosine of theta plus phi, and the imaginary part is identical to sine of theta plus phi. And so this is cosine of an angle plus I times sine of the same angle, so we can re-express that as e to the I theta plus phi from its definition. So e to the I theta plus phi equals e to the I theta plus e to the I phi. And we will need to use this sometimes for phases. Now, this is the same as if we do real numbers, e to the a plus b, where a and b are real numbers, we would be able to multiply e to the a times e to the b. So this is not a new thing to remember. It's just that something that we know how to do in real numbers, we're also able to do in imaginary numbers. And so that's pretty handy. Now, there are hundreds of trigonometric identities. You won't remember them all. I don't remember them all. Here's a nice website if you ever want to know some identity, such as the ones we used above. But we're not going to use too many identities in this course. And if we do, I'm going to give you the identity. I'm not going to have you guess it. So we could take this formula above and we can just negate phi, and it would negate here and it would negate here. So e to the I theta minus phi is e to the I theta times e to the minus I phi. Now, let's take this formula and replace theta with phi. So we get e to the I phi minus phi equals e to the I phi times e to the minus I phi. But phi minus phi is 0 and e to the 0 is 1, so this is 1, so e to the I phi times e to the minus I phi is 1, so e to the minus I phi is 1 over e to the I phi. This is a possible time to take a break. Now we can always choose to express any complex number, u equals a plus bi, in terms of its magnitude and argument or phase, as follows. U equals magnitude of u times cosine theta plus I sine theta, where theta is the correct angle for u. Or alternatively, u equals magnitude of u times e to the I theta, where the magnitude of u is square root of a squared plus b squared, and tangent of theta equals b over a, and we have to take care which quadrant theta is in. You may sometimes see that theta is the argument of u, or in computer language, theta can be calculated as a tan 2, a particular arctangent function of b comma a. We won't have to use this, but you might want to know it. Now, the complex conjugate of u is u star equals a minus bi, and we can express that as u star is magnitude of u times cosine of theta minus I sine of theta, because the imaginary part gets negated, or alternatively, from this form, u star equals magnitude of u times e to the minus I theta. Same magnitude as u, but the angle or argument or phase gets negated. Now that we have that, we can multiply u times its complex conjugate, u star, and we get magnitude of u times e to the I theta times magnitude of u times e to the minus I theta. We can rearrange this. We get magnitude of u squared. The e to the I theta and e to the minus I theta, they multiply together to get 1, so u star equals magnitude of u squared, as we've seen before. This is a possible time to take a break. Now we can express complex number v equals c plus di in terms of its magnitude and phase. Same as before, it's just magnitude of v, and we have to use a different angle phi, because we've already used theta. Now we can express the product of complex numbers u and v using this complex exponential form. uv equals magnitude of u times e to the I theta times magnitude of v times e to the I phi. We can rearrange those. We get magnitude of u times magnitude of v times e to the I theta times e to the I phi. We can combine these last two, so we get magnitude of u times magnitude of v times e to the I theta plus phi. We get the product of two complex numbers by multiplying their magnitudes and adding their phases. And often this is easier and nicer than using the A, B, C, D form. We can express the quotient of complex numbers u and v U is magnitude of u e to the I theta, v is magnitude of v e to the minus I phi. We can move the e to the I phi in the denominator, we can move it to the numerator by negating the phase. We can combine these phases, so we get that the quotient of two numbers, complex numbers, this should say dividing their magnitudes and subtracting their phases. This is when v is not 0. So this should say dividing. We can express the cosine and sine functions in terms of complex exponentials, and sometimes this is very handy in quantum mechanics. So we already know that the formula for e to the I theta, we know the formula for e to the minus I theta, because cosine of minus theta is cosine of theta and sine of minus theta is minus sine of theta. If we add these together and divide by 2, we would get cosine of theta equals e to the I theta plus e to the minus I theta over 2. And if we subtract them and divide by 2i, we get that sine of theta equals e to the I theta minus e to the minus I theta over 2i. You won't have to remember this. I will use this and I'll point it out to you, but you won't have to remember it. This is a possible time to take a break. We can use complex exponentials to determine powers and roots of complex or real numbers. Though we might not need to do this in our quantum mechanics lectures, I'll just mention it here. It is a very useful result in complex numbers. So u to the n is magnitude of u e to the I theta. Quantity to the n, we can rearrange this to be magnitude of u to the n and e to the I n theta, where n is an integer. If you don't follow this, you could start out with n being integer 2 and see that it's true, and you can build on that. This is called de Moivre's formula. There's also a formula for roots, square root, cube root, and it is this formula, and this gives the nth complex roots of a complex number or a real number. We won't use this, but it is a result in complex numbers. Sometimes an exponent of an exponential might be the sum of a real number plus an imaginary number, such as e to the sigma plus I omega, where sigma is real and omega is real. This will equal e to the sigma times e to the I omega. We won't prove this, but it is a result in complex numbers. This is the end of lecture B8.